All right, it's the last one. It's physics 2, and I've got my rainbow of marking pens here. I'm going to really try to actually do different colors as often as I can. Anyway, reminder that this is brought to you by World's Finest Physics. We're doing a physics summer institute type thing. It's going to be lots of hands-on, how you can incorporate toys and things like that in your class. It's not physics 2 though. We're going to do mechanics this year. It's our first our first outing. If it's popular enough, we might include Physics 2 and E&M type thing in a future summer. But if you're interested, somebody's interested, there's a website or you can contact me. All right. There we go. That's the hour. It's chiming right there. Okay. Let's see. So you got a block on a string. Wow. Somebody get that block a sandwich. Okay. Students are it's just so tiny. Electromagnetic wave phenomena in transparent media. You use a string to support a stationary rectangular block. The block has two narrow slits. Oh, so this is actually a slits question. I thought this was going to be a buoyancy question. Well, it looks like they're setting us up for a buoyancy question. Yeah, they're setting us up for a buoyancy question. So here's what happens. What they do is they say that the whole free response in total has to have a certain number of points for each unit, right? So what happens, you get to the last question that you write, which in this case, whoever wrote this is the first question that they wrote. Or no, I mean, it was the last question they wrote, but it was the first question on the free response set. And that's where you're like, oh, crap, I need 3 more points for fluids. And I also need like 6 points for optics. So crap, how am I going to do that, right? Well, you come up with something as convoluted as this. That's what it's like to write AP free responses here. So draw and label forces. So you're going to have a good old mg. You're going to have a good old force buoyancy. And you're going to have a good old force tension. Driving expression for the force exerted on the block by the string. So tension's up, buoyancy's up, mg is down. Now, tension's what I'm looking for. That's what I'm looking for. Buoyancy is the density of the fluid, the density of the water. The volume that's under the water is the volume of the whole block, G. And remember, mass itself is density of the object itself. Oh, wait a minute. Am I allowed to just leave it as MB? Oh, I think I can just leave it as MB. Okay, G. Okay, so I'm going to subtract force tension equals mass of the block G minus density of the water, volume of the entire block that's under the water, gravity, and we're good to go. All righty then. Now it's time for the optical stuff, it looks like, because it says a monochromatic laser beam. Remember, I'm seeing this for the first time, although I did look at the images when they were coming out of the copy machine. Incident perpendicular to the wall of the tank. The beam passes through the slits of the block. An interference pattern on the other side. Great. The water is then replaced with a clear fluid with greater index refraction than that of the water. Clear, coherent paragraph length response. Describe how the greater index refraction affects the interference pattern. Okay. So let's see. This is where I'm going to bust out my ABCD method. So A stands for answer. I'm going to answer the question. And this will be good to do on another place, like at the back where it's blank and you can plan your answer if I was a student. But I'm in a hurry because I got to go to the bathroom. So I'm going to just wrap this up. So A is for answer. I don't know the answer yet. B is for basic physics. Okay, so what are some basic physics? Basic physics could include basic equations. So here's a basic equation. D, which is the slit spacing, sine theta, that's the angle of the interference maxima, equals M, which maximum are you talking about? 0, 1, 2, 3, and the wavelength of the light. So that's one equation. And then another equation might be this. I teach my students this. N lambda equals M lambda. So frequency is the same, but N sine theta equals N sine theta. So N and sine theta are inversely proportional. N lambda equals N lambda, and N velocity of the light equals N velocity of the light. So those are 3 equations. So N sine theta, N1 sine theta 1 equals N sine theta 2. N1 lambda 1 equals N2 lambda 2, and N1 V1 equals N2 V2. So index refraction is inversely proportional to wavelength and speed and sine of theta. Frequency stays the same. Frequency is not affected by index refraction. So I'm going to say this is the initial N in lambda. This is the final N in lambda. And it says a fluid with greater index refraction is going to be a smaller wavelength. Okay, so now here comes some basic physics. If the index refraction is greater, the wavelength is less. Actually, this might be C. This is when we actually connect to this problem. Again, the lines are blurred, but it's just something I teach students, like guess for problem solving. Answer the question, say basic physics, which could include basic equations, things that are true all the time. Now connect to this specific problem. Also, C stands for compare and contrast. So you can compare, say what's the same, and contrast, say what's different. So if n is greater, the wavelength is less. If the wavelength is less, but the slit spacing is the same, then the sine theta is less, and the maxima are closer together. Okay, so I'm going to say the bright spots are closer together. D stands for draw your ideas back to your assertion, to your answer. I kind of feel like I did that here. So again, if your students are really good at writing for physics, they do this naturally without even having to think about it. But almost nobody is good at physics. So I give it to them as a check. Hey, did you answer the question? I don't care if you did it first. Just did you answer the question directly? How does the index refraction affect the new interference pattern? Did you answer the question correctly? Did you say some basic physics, which could include a basic equation? These are things that will always be true. They could be F net equals ma. They could be more mass means less acceleration for the same force. That's the same basic physics. That's still Newton's second law. It could be force and acceleration are directly proportional. That's also Newton's second law. So those are all equivalent ideas. Connect to this problem, cite important information, compare, contrast. C is when you talk about what's going on here in this one. B is always true, but C is true in this case. D, make your B and C connect back to your A. And a lot of students just draw their points together and then say the answer. Okay, and then answering the question sometimes involves checking a box or checking a mark, Okay. The block is replaced by a prism. The path of the beam indicated by the dotted line. Okay, so I'm going to draw a little normal here. So let's see what my little normal here looks like. I think that if this bends down, this angle is bigger and this angle is smaller. So that means that the prism is the higher end. This is going to be the lower end material. Okay. The fluid is then just removed from the plank and the prism is surrounded by air. So now the lower end is even lower. Will the beam above, below, or so I'm going to, again, answer the question. And this answer I already know is going to be below point P. So there's my answer, right? Basic physics is going to be N outside sine theta outside equals N prism sine theta prism. Okay, so what do? We reduced N outside. Okay, we reduced the N outside. So the theta outside must be greater, right? The outside used to be the water, but now it's the air. So the theta outside must be greater. So the beam bends down more and reaches the screen below point P. So there you go. Answer the question. Basic physics. Connect to this problem. Draw your ideas back to your answer. And it doesn't, and again, this is something you can do on the very last page. It's on the one that you can do on like this blank page or whatever, any scratch work place, especially for the paragraph length response. I would endorse that. All right, so that's my structure for writing. Doesn't have to be in that order. Just has to be an order that makes sense. It's a checklist. Did you answer the question? Did you say basic physics, basic equation? Did you cite important information? Did you draw your ideas together? All right. Students perform experiment battery for resistors A, B, C, D. Okay, let's switch to maybe pink now. The resistors B and D are 2R, A and C are 1R, so R, and let me do this in a different color, 2R, right? Okay. From greatest to least, rank the magnitudes of potential difference. 1 with the greatest. Okay, so one for you. This is my answer right here. And then for C and D, it's going to be D is the next, then C is the last. Okay, so what am I going to say? And so this is the answer. I'm not going to write B, C, and D anymore, but you're going to see the pattern. We're going to say, voltages in parallel are the same. That's basic physics, right? So A and B in parallel with the battery have the same full voltage as a battery, but voltages add in series. So delta VC plus delta VD equals the V of the battery, right? Okay. So what am I going to say? I'm going to say I is the same in series. So since V equals IR, more R is more V. Okay, so more V, maybe I should write right there. So VD is more since RD is more. Okay, I feel like I've beaten that horse to death. In another experiment, students have a capacitor with an unknown capacitance. Want to determine the unknown capacitance using a battery with 4.5 volts. Other capacitance, a known capacitor. They create circuits with the battery. Unknown capacitor. The students wait until the capacitor is fully charged and record potential difference. Their data is shown on the following page. Okay. Calculate the amount of charge on the capacitor of known capacitance, 200 microfarads in the student's experiment. Okay, well, Q is equal to CV. The C is 200 microfarads. The V is 0.91. Now I want to know where my calculator went. What I do with my calculator? There it is. I should honestly be able to do this. Should be like maybe 1.82 or something. So 200 times 0.91. Yeah, 182. So 182 microcoulombs. Briefly explain why the data in the table of front evidence capacitors are connected in series. On each row, the V's add to 4.5 about. Okay. Voltages add in series. Okay, I was about to say this up here. I'm going to, if the C's were in parallel, then all voltages measured would be 4.5 volts of the battery, right? Regardless of the capacitance of each capacitor. Okay, so there's no variable there. Okay. The students want to produce a linear graph of the data so that the capacitance unknown can be determined from this. Okay, so how am I going to do this? Okay, so we know that these two things add to 4.5, but here's what else we know is that in series, capacitors have the same charge. So here's your battery. Yeah, I know my battery symbol looks different than everybody else's. Shut up. All right, so C known, C unknown. And what we know is we know the Q equals CV is going to be the same. So C known, V known is going to equal C unknown, V unknown. Okay, so we have one unknown and three variables. So here's what I'm going to say. What I'm going to say is I'm going to say the Q is going to be the Y, and the C unknown is going to be the slope, and the V on the unknown is going to be the X. Okay, so what are we calling these? Delta VU. So on the vertical axis, delta V VU in volts. And on the horizontal axis is going to be Q, which is C known, delta V known, and that's going to be in microcoulombs. Okay, so the Q is equal to C known, V known, and it's going to be in microcoulombs. Okay, so here we go. I feel like making this faster. 2, 3, 4, 5, 6. Okay, L1 times 200. Oh, no, I didn't mean that. L1 divided by 2 is what I meant to do. Okay, there you go. And then we have 0.91, 0.65, 0.51, 0.42, and 0.36. Okay, so now I'm just going to do CV. All right, so I'm going to get 182, 195, 204, 210, 216. And what was I going to do? A delta VU on the vertical axis. So then I'm going to say that my plot here, it's junk from who knows when, my plot here is going to be X list is going to be L3 and L3 and then L2. So let's turn that on. Zoom 9. Okay, so I get what looks like that is not promising at all. That is not making me happy. That I want. All right, so that was V. Oh no, it needs to be versus V unknown. Ooh, okay. I was about to do something dumb. Okay, so there's and then V unknown. That's 3.53, 3.74, 3.95, 4.06, 4.17. Yeah, nothing like a negative slope to make you say WTF. Zoom 9 now. Okay, it's looking good to me. How about I do like a little linear regression because that's what I feel up to today. Okay. Okay. All right. So, and then what else do I want to do? I want to figure out how am I gonna plot this? So I need to go from 3.5 to maybe 4.5. Gosh, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I've got 16 of these spaces. So if I do 3.5, 3.6, 3.7, 3.8, 3.9, 4, 4.1, 4.2. Okay, 3 points. This is horizontal? No, this is the vertical axis I should be looking at. 2, 4, 6, 8, 10, 12, 14, 16. Okay, well, that's the same thing. So 3.6, 3.7. Wait a minute, I didn't mean 3.6. I meant 3.5, 3.6, 3.7, 3.8, 3.9, 4.0, 4.1, 4.2, 4.3. Okay, I guess that's how I'm going to play this game. And then the charges. Okay, 180, 190, 200, 210. See, I'm not going to use all the space, am I? Should I use maybe 180, 185, 190, 195, 200, 205, 210, 215, 220? I think that's going to work. So this is going to be Q in microcoulombs. This is going to be delta VU in volts. All right. So let's see. 180 to 220, go by fives. Yeah, this is the part where you find out I don't actually know how to make a graph. I have to use a calculator to do it. Isn't that kind of sad? It's what a sad commentary that is on our society. Okay. I am super not doing anything right here. Okay, I think I swapped what I meant to do. Did I swap what I meant to do? Where's the sheet where I worked this out? Now the Q was supposed to be the Y. Well, it's the reciprocal of the slope then. Okay. Oh, goodness. Okay, well, that's just life, isn't it? All right, so not only do I not know how to make a graph, I really don't know how to make a graph. Okay, so 180, 220 by fives. Okay, so there it is. Looks beautiful. Okay, so all right, so 3.53 and 1.82. Okay, maybe there. And then 3.74 is almost there. 195 is there. All right, so 3.95 is there, and 204 is about right there. Okay, 406. This is so tedious. I mean, it's easy points for your students, but it feels just tedious. Okay, got my golden ruler here. Has the golden rule on it. My favorite thing to do with my golden ruler is to beat the tar out of my students when they misbehave. Okay, let's see. All right, so the slope of this monstrosity here, did I even have it here? Okay, so the slope, I actually had the slope in reverse here. All right, so slope is 0.01919 found with TI 84 calculator. Okay, and then I did this wrong. It's actually going to be, this is going to be the reciprocal. This is 1 over CU. So CU is 1 over 0.01919. 1 over, if I could get that right. All right, so that's 52, and that's going to be in microfarads. So it's going to be in microfarads because everything was in like microcoulombs and things like that. All right, that was annoying, and I couldn't think straight. Obviously, I labeled everything wrong and whatever. You want to be more careful than this, but I'm in a hurry because I've got to go to the bathroom. All right. Derive an equation of speed via the electron, which we're modeling as a little planet orbiting the proton like the sun. So we're going to say a K physical constants be like E. So K E E over R squared equals the mass of an electron. That's a physical constant. V squared over R. R partially cancels. And you get K E squared over MR equals V squared. So V equals the square root of K E squared over MR. Total energy is going to be 1/2 mv squared. This is basically an AP Physics 1 question. Minus KEE over R. So what am I going to get? I'm going to get 1/2 mass of the electron, KE squared over MR minus KE squared over R. The M's cancel. I get a half minus a whole. So the energy will be negative 1/2 KE squared over R. All right, whatever you want to do with that. When the hydrogen atom absorbs a photon, the electron moves to an orbit with a larger radius and the total energy increases. Is your equation for the energy derived in part B consistent with this description of the model hydrogen atom? Yes. If R increases, then E total is a smaller negative. It's a smaller sized negative, all right, which represents an increase in E total. All right, experiment show the hydrogen atom can absorb a frequency of that. Calculate the energy of a photon with this frequency. Okay, so that's just a little E equals H. And what the heck is H anyway? I forgot my value of H. Where is it? Okay, 6.63 10 to the negative 34, 3.2 times 10 to the 15. I'm hoping I don't need to be in electron volts. 6.63 10 to the negative 34 times 3.2 15. So the energy is going to be 2.1216 times 10 to the negative 18 joules. Okay, should probably be swapping the colors around. Student claims that when the hydrogen atom absorbs this photon, the energy could be converted into mass. Adding an electron to the atom, no way. Here's why. E equals mc, is that asking? Calculate the amount of energy needed to create the particle with the mass electron. Okay, so this is 911 10 to the negative 31. This is 3 times 10 to the 8th. This is going to, it's going to look like a small number, but it's going to blow the other number out of the water. And it's 3e8 squared. And so we get an E of 8.2 times 10 to the negative 14 joules, which is almost 40,000 times more energy than the photon carried. So no, you cannot use that photon to create an electron. Even if you did, you would be violating, even if you could create an electron, that would violate conservation of charge. Because where'd the equal positive come from? You created the negative out of nowhere. Okay, the left bar chart is complete, represents the initial electric potential energy of the atom, and kinetic energy. In the space provided on the right, draw a bar chart represent the possible final potential energy of the atom, the final kinetic energy of the electron. Okay, so I'm going to say that energy is K plus U. So energy was negative 1/2 KE squared over R. And we just said that the R is going to increase. Right. And then that must be because the kinetic energy is 1/2 KE squared over R, and the potential energy is negative KE squared over R. So let's pretend for a moment that the R gets multiplied by 2. Let's say that the R gets multiplied by 2. then this would be half as much, this would be half as much, and this would be half as much. So then you would have half as much potential energy, but also half as much kinetic energy. And if you look carefully, the total energy is actually greater. The total energy is actually greater. I think that's it. All right, sure, why not? Constant velocity, wire, carrying current. Region contains uniform electric field, and distance d from the wire. Driving expression for V in terms of that stuff. Okay, so the FE is equal to the FB. All right, so we got that down. I think we're clear on that. The FE is going to be QE. E is something I'm allowed to have. Q is a charge on whatever it is. Equals FB. That's going to be QVB. So the Q's cancel. The E will equal V, and what's the B? Mu naught I over 2 pi distance. All stuff I'm allowed to have. So the V is going to be 2 pi distance electric field over VB. Great. All right, I think that's wrong. What was I looking at? It's over mu naught I. Over mu naught I. Sorry, I looked at the wrong equation for a moment. The charge object's removed, square coil, side length 2L's, placed along a straight wire. Bottom of the coil is distant L. This sounds like physics C problem. And the magnitude of the magnetic field due to the wire is 3B naught at point P1 and B naught at point P2. Write an X at the location where the magnitude of the magnetic field is 2B naught. Ooh. It's going to be here. Because 1L makes 3B naught. 3L makes 1B naught. So how do you make 2B naught? This is an inverse proportion, so I think this has to be 1.5L. Yeah, see, it's inversely proportional. So 1 times 3, 3 times 1, and 1.5 times 2. All multiply to the same thing. Briefly justify your reasoning. B and distance from the wire are inversely proportional, right? So if 1B naught is 3 L's away, then 2B naught is 1.5 L or half as far. All right, so that's justify my reasoning. Over a time interval, the current in the wire is decreased. The initial magnetic flux is that. Oh, we don't have to integrate because this is not physics C. The final magnetic flux is that. All right, the coil has a total resistance. Calculate the average current. Okay, so EMF is 2 things: a negative delta flux over delta time. It's not physics C. And I times R. So what's the flux is a magnetic field. Oh, no, we're given the flux. So it's going to be, and I'm not going to worry about it. So it's basically 5 minus 1 times 10 to the negative 5. The time that took was 2 equals I. The R is 10. So the I is going to be 4 times 10 to the negative 5 over 20. So what is that? 40 negative 5 over 20. All right, I is 2 times 10 to the negative 6 amps. All right, the wire's removed and the square coil is positioned so that the coil is directly above and concentric with a round coil wire connected to the power supply. A part of the square coil is removed. Okay, and a light bulb is connected to the coil. During a short time interval, the current in the power supply is constantly increasing. Use physics principles to explain why the light bulb is lit during the entire interval. So I'm just going to say, all right, well, the coil creates upward or downward magnetic field, which links, by the way, that's the verb, by the way, links magnetic flux through the square, okay? If the I in the round, I should call it the round coil, there are 2 coils, in the round coil changes, the B changes, and the flux changes. Okay, if flux changes through the square coil, then on EMF is induced, and the bulb can be lit. And that's the end. All right. I hope you enjoyed this set of, 6 for mechanics, 6 for EMAG, that's 12, plus 5 for P1 plus 2. So 12 plus 9, these 21 free response questions. All right. I'll see you at the reading or next year.